Hello and welcome to another session of Introduction to Astrophysical Fluids. In the previous discussion, we talked about the generation of the stellar winds, and also we said that this problem is equivalent to its inverse problem in the steady state, and this inverse problem is the famous Bondi's problem of spherical accretion. We also mentioned that this is an ideal case. In reality, no accretion, no mass accretion in an astrophysical system basically follows this type of isotropic accretion, okay, using spherical symmetry. In general, what happens that whenever a less dense star comes in the vicinity of a very dense and compact star, okay, it loses mass, but this process actually leads to the formation of a disk type of thing, and that is known as the famous accretion disk in astrophysics. In this discussion, in today's discussion, we will mainly try to understand qualitatively, okay, how the the accretion disk is formed, and how due to the formation of the accretion disk some energy can be released. So, as I want to emphasize that in astrophysics, very often viscous effects are neglected. Okay, so although we said that we started discussing different astrophysical examples after deriving the real fluid equations, which includes different type of transfers. Okay, so you can actually see that very often viscous effects are neglected in astrophysical problems. But remember, this does not say that the fluid is perfectly ideal. There is always a non-negligible transfer of the thermal energy, and that's why if you remember that the divergence of K gradient of T term, that is always non-vanishing, almost always non-vanishing. Okay, but however, the thing which we are talking, that is the viscous effects, this is somehow neglected in the very usual problems of the stellar wind, for example, or the evolution of the star forming gas spheres. So for the stellar wind, we already saw that in Parker's model the viscous effects are neglected, and for the evolution of the star forming gas spheres, maybe you know that we just consider mostly the equilibrium due to the interplay of the pressure gradient force and the self-gravity force. Okay. However, there is one particular example where viscous effects must be considered, and they play an important role in the formation of that astrophysical structure, and that is the case of the accretion disks. Okay. So, most interestingly, not only that we should include the effect of the viscosity in case of accretion disks, but also the coefficient of viscosity mu, if you remember it, okay, is no longer a constant for a given fluid. This is not a constant in space. Okay, so we shall come to this later when we will talk about the analytical approach using basic equations. But before discussing this dynamics part, okay, using analytical approach or using equations, okay, we first try to understand what happens during the formation of an accretion disk, and actually very primarily why an accretion disk is formed. Okay, that we will try to discuss in a very simplistic way. Now, in astrophysics, it is true that there are two types of mechanisms which principally produce energy. Okay, one is the famous nuclear reaction, we all know about that, and the second one is the loss of gravitational potential energy. Okay, and that lost energy basically gets transformed or converted into a radiation. Okay, that is possible. So, for example, when we are talking about the evolution of the stars, then the first mechanism, that is the nuclear reaction, is the principal source of energy. For this type of system, the lost amount of the the amount of the lost gravitational potential energy is actually negligible over the nuclear component. But when a less dense star with bigger volume, now you can see in the picture, okay, that is a good thing to see a schematic picture. Here you will have this. So this is the less dense star but with bigger volume, this one, okay. When this comes in the proximity of a dense and compact star, okay, this is this one, the very small one, okay. Then the less dense star basically loses its gravitational potential energy, okay. And what happens? An inflow of matter from the less dense to the dense star happens. So basically the mass is coming from this one and going to this. But how does it goes towards this mass? Not like in a linear way or something in a spherical way, but in a spiral way, forming in a disk. That is what is somehow a known phenomenon. Okay, now we have to try to first of all understand why this is happening. Okay, but even before that, we will do a very simple estimate to just show that unlike the case of a star evolution, where the nuclear energy component basically dominates over the gravitational potential energy loss, okay. Here in the case of accretion disks, this is not the case. This is the primary reason of the energy production, or primary source of energy production, because there is no a priori source of nuclear energy, okay. So for that, what we can do is that we just can consider a typical dense star with mass which is equal to 1 solar mass, okay. So maybe you should have an idea of what 1 solar mass is in terms of kilogram. So you just check and you will tell me whether it is nearly 10 to the power 30 kilogram, or 10 to the power 31 kilogram, or 10 to the power 32 kilogram, or what else, okay. So that is something you have to search it out, okay. So if it has a mass equal to 1 solar mass, but the radius is only 10 kilometer, so you can see that the total mass of the sun is only contained in a sphere of radius 10 kilometer, then the density is enormous. That you should also calculate, okay. In this case, the loss in gravitational potential energy for that mass, so here we are talking about the mass of this one, this small star, okay. This has this mass 1 solar mass. This one is losing the mass, okay. So in this analysis, if you see that the loss in gravitational potential energy is given by G times 1 times m solar. So that I just wrote like as m solar, okay. So this is the unit of m solar, so I just wrote like this, okay, times m, which is the mass of this star, less dense star with bigger volume, by the radius, okay. So that is the part, that is the thing, that is the amount of gravitational potential energy which is lost when the mass starts leaving this body and really reaches this body, of course, okay. And you can easily, just by multiplying c square, where c is the light speed at vacuum, you can write this factor as gm dot c square by c square a, this ratio, times mc square. And mc square is nothing but roughly the rest mass energy of this star which is losing mass, okay. So now the question is that this one is the amount of the lost gravitational potential energy, and this one is its rest mass energy. So the ratio of the two will simply be this one. If you calculate this factor, you will see this will give you 0.15. Please check that. Okay, I hope there will be an exercise also for on that in the assignment. Okay, so that means that the loss in gravitational potential energy is about 15% of its rest mass energy, which is considerable. Okay, so then we finally could show that in this case of the formation of this accretion disk, that means in the case where the mass is lost from in a binary system of a less dense star and a highly compact star, okay, basically the loss in gravitational potential energy is a considerable source, although we could not compare this with nuclear reaction, but is a very, considerable source of production of energy. Okay, and then actually okay, I'm coming to this, but before that, so now as we already mentioned that the mass from the less dense star does not create an influx in an isotropic way, that means like a spherical accretion. Okay, so this type of thing will never be accreted like a sphere, but the accreting matter, which has an angular momentum, indeed forms a disc-like structure. Okay, once again you can just see this figure for reference. Okay, so this is the disc which is formed over here. Okay, and the mass which is leaving this original volume is now going towards this mass in a spiral path. Okay, so if we concentrate on a mass element on this accreting matter, we will just see that it spirals inward from the less dense star to the denser one, thereby losing gravitational potential energy. Because basically what is happening, this some amount of mass is now falling in the gravitational attraction gravitational field of this star, and this field being attractive basically makes this system lose its gravitational potential energy. Okay, because the system is doing work supporting the attractive field. Okay, so basically the system is losing the gravitational potential energy. But the question is, what happens to this lost energy? The lost energy is then radiated and usually is manifested by X-ray sources in the astronomical observations. Okay. Now, some historical information. One is that the first detection was made in 1962, and this type of detection was much easier later when a satellite Uhuru in the year 1970, 8 years after the first detection, was launched, and which was completely dedicated to X-ray astronomy. Okay, now some galaxies, of course, now it is a question that why we should study accretion disks in astrophysics, why basically the accretion disks are at all important or at all interesting. Because some galaxies contain very compact sources of huge amount of energy radiated in the form of X-rays. Okay, now such sources are called active galactic nuclei. Okay, and a very good example of that is the quasars. Okay, you can search over internet to know what quasars are. Okay, so what is active galactic nuclei? Active galactic nuclei is nothing but a very localized part of a galaxy which produces an enormous amount of energy. Okay, and the wavelength is already almost always in the X-ray domain. So active galactic nuclei, that is actually modeled as an accretion disk around a supermassive black hole at the galaxy center. So you understand what is the meaning of that? Just I said that active galactic nuclei is a very local, is a very compact space or a very local part. Okay, a part with very small volume inside a galaxy. Okay, inside a galaxy, let's say we have a spiral galaxy like this, and inside this galaxy, okay, near the center, let's say it has a very short volume from where you can found an inner mass ejection or an inner mass ejection of energy or radiation. Okay, let's say X-ray radiation. Okay, then people actually could study its property by modeling this as an accretion disk around a supermassive black hole. That means, here this type of active galactic nuclei can be modeled when this compact star is nothing but a black hole itself. Okay, and which is situated at the center of the galaxy. Okay, that is the famous Lynden-Bell model of 1969. If you are interested, you can see the original work. Okay, and basically, of course, this is in the scope of this course. I encourage all of you to study different original research papers to see that what these people have done, and that is also a very good occasion to cross check that what I have discussed here is really exactly the same of what is inside the paper. Okay, so due to enormous importance in astrophysics, for example in modeling this type of active galactic nuclei, okay, it is highly necessary to know the dynamics of accretion disks. That was the importance. Okay, now before coming to the other points, one thing is very simple, that in most cases when the accreting matter is moving around the dense star, a reasonable approximation is to assume that the any mass element which is now getting accreted, okay, in a spiral path should follow a Keplerian motion around the dense star. What is the meaning of Keplerian motion? The meaning of Keplerian motion is like there's a motion of a planet around the sun. That means the balance, okay, the force balance on this body will be just due to the interplay between the gravitational attraction force between that mass element and the dense star, or the center of attraction here. Okay, and which will be basically counteracted by the centrifugal force, which will act outward, radially outward. So gravitational force will be attractive, so it will be radially inward. Okay, so if you follow this Keplerian type of motion, then one thing is evident, that due to Kepler's third law, the angular velocity, or you can directly see from the force balance, actually both are correct, okay, both are equivalent, that angular velocity should have a dependence on the radial distance from the center of the attraction, okay, like this. So that means omega should be equal to some gm. So g is the how to say, so g is the universal constant, gravitational constant, and m is the mass of the center of attraction, and this r is the instantaneous distance between the mass element and the center of the attraction. So the omega should be, capital omega should be written like this. This is the angular velocity of the mass element. So capital omega has this type of radial dependence, and this type of disk is known as Keplerian disk. Now, in order to tackle the problem of accretion disk analytically, okay, people tried to do this, tried to make this much more simpler using some reasonable approximation. So one approximation was very handy. That was the approximation of a thin disk. Okay, that is, the thickness of the disk is neglected for considering the dynamics of the disk. That does not say that the disk is purely two-dimensional, but it simply says that the dynamics of the disk, okay, that means the mass motion can sufficiently be studied in one layer. Okay, that means that even if the disk is thick, if one just studied that one layer, the what is, I mean, maybe you can see that this type of thing is actually consisting of very, I mean, a number of this type of spiral paths, and if which are basically, I mean, you can see like this as roughly stacked over one another, and if you like this, okay, and if you know what is happening at one layer, this is sufficient. Okay, so that is one possibility. And then another point is, of course, if the disk is really thin, okay, if the disk is really thin, then of course the thickness is absolutely neglected, both structurally and also dynamically. And then trivially you can have only a 2D type of sheet type of thing, and you can see that this type of thin disk approximation is very much valid, and this is useful especially because this makes the mathematical approach I mean a lot easier. Okay, that was proposed by two scientists, Shakura and Sunyaev, in the year 1973. Actually, you can see their paper as well. Okay. Now, Keplerian motion implies that different layers of the disk have different angular and orbital velocities, because angular velocities are already dependent on the radius. So it is you to think how, if angular velocity has this type of dependence, then how the orbital velocity, which is v, and that should have a radial dependence. Okay, you will see that we'll also have a radial dependence such that this will increase when r decreases. Okay, so both the orbital and the angular velocities, they are I mean they are higher for inward orbits and they are lower for outward orbits. Now this is the very important point. Now if we consider that the fluid is viscous, then what happens? As the disk is made up of different layers, okay, having different angular velocity and different linear velocity, of course it's the same thing over here, I mean this is somehow equivalent. Okay, then what happens, that they should have a they should have a relative velocity, relative orbital velocity, and relative angular velocity as well. Okay, and whenever they have a velocity gradient, okay, if they have viscosity, viscosity will try to reduce that gradient by exchanging either angular momentum or linear momentum. Okay, so in order to reduce the linear velocity gradient, linear momentum is transported from the faster moving layers to the slower moving layers. And if angular momentum, I mean if there is a gradient for, I mean to reduce the gradient of the angular velocities, angular momentum is transferred from faster to slower moving region. And what is the meaning of that? That means from inside to outside, right? Now once so the angular momentum is transferred from inside to the outside, then the layer inside would lose angular momentum. Okay, now to maintain the Keplerianity, I mean that is very important to maintain, because otherwise the force balance would be destroyed. The angular momentum should have radial dependence as this. Okay, so both omega and v, they have such radial dependence so that they are increasing when r is decreasing and vice versa. But if we are considering about L, which is nothing but m r square omega roughly, then you can actually see finally L has a linear dependence of root over r. Okay, So that means when R increases, L is also increases. So in general, so if let's say some mass, some layer, some fluid layer in a given radius loses its angular momentum, okay, that means it has now a lesser angular momentum. So that means this, with this angular momentum, this mass element will be eligible to be in an inner layer corresponding to another R which is less, okay. And then the layer at a certain radius, so as I just said, loses angular momentum, it has to go to less R, that is inward. But how it goes inward? It goes in a spiral path, okay. And that finally, so when it goes inwards in a spiral path, what is the meaning of that? Spiral path is of course necessary, because otherwise the Keplerian it will not be there, okay. And when it go, I mean whatever be the path, finally the thing is that the mass element is going closer to the central body. What is the outcome? There will be a release in gravitational potential energy. Clear? Now you see that it is only the viscosity which controls the radial inflow of the matter. So let's say if the system, okay, if the fluid does not have any viscosity, so then even if there is a, I mean, velocity gradient or angular velocity gradient in two successive layers, I mean, there is no necessity for the system to transfer, I mean, to transfer angular momentum from one layer to the other. It is only due to viscosity this is possible. So in the absence of viscosity, this mechanism would have been absent. So it is the viscosity which actually controls the radial inflow of matter, and therefore it is controlling the rate of the energy released, because the rate of the energy actually released because of the whole mechanism, right? This will be much more evident when we talk about the analytical results. Okay. Now finally, I mean, we will go to analytics. Okay, we have said that I mean, we will do analytics after doing some qualitative discussion. So now the qualitative discussion is over. So we have somehow a rough idea, rough picture that how the accretion disks are formed, okay, and how due to the formation of the disk, finally some amount of gravitational potential energy is released, okay. We will now switch to do some analytical treatment, and for that we have to write equations, but even before that we have to talk about the basic assumptions. So now we first discuss the basic assumptions needed for an analytical understanding of the accretion disk dynamics. Okay, so here there are a list of assumptions, and all of them are equally important. First assumption is that this is a disk, so this is not a sphere. So I mean, intuitively this disk is axisymmetric, okay. I mean, intuitively whenever it's a disk type of thing, now which coordinate system should be the most appropriate one? Of course not the Cartesian, neither the Cartesian nor the spherical one, so it should be the cylindrical coordinate system. Now the disk is considered to be axisymmetric, okay. That is somehow, sometimes it is coming from the disk itself, but what it is saying that inside, I mean in the plane of the disk, not only the disk is in a disk shaped, but I mean in the plane of the disk, what happens that if you if you I mean, let's say you have this type of plane of the, I mean, disk. So in this plane, okay, if you just fix your radius from the center, okay, then everything will be same. So the phi coordinates of this cylindrical coordinate system, that means are, there is, I mean, not phi but theta, sorry, theta coordinates r, theta and z, they constitute, sometimes we call, some in some literatures it's called phi. So theta coordinates, okay, and the z coordinate. So here these are the three coordinates for a cylindrical system. So when we say about axis symmetry, it says that it does not depend on theta. Okay, no properties will depend on theta. So in the plane of the disk, okay, it's everything can only change as a function of the radial distance from the center. Okay, and that's why del theta is 0. Del theta of anything is 0. Okay. The third one is the principal motion of the moving matter is in the cross radial direction, that is along theta cap. Okay, and what is the meaning of that? That means that the v theta is very greater than vr, and of course of vz as well. Okay, because we have not said anything about vz, I am just saying it. V theta is the dominating component. Vr is small but non-zero. That is also important, because Vr is necessary to produce the small radial inflow of the matter. It causes mainly a small radial flow due to viscosity. Okay, so Vr should be there, and no motion along z direction. Okay, so that is somehow an immediate outcome of a thin disk approximation. So if the disk is very thin, then along z direction no motion should be expected, no considerable motion. So just a very good approximation, reasonable approximation is that Vz is equal to 0. Okay, so V theta is the biggest one, Vr is the smallest one, I mean not the smallest one, sorry, V theta is Vr is a smaller one. Okay, but both of them are non-zero, but Vz is 0. Okay, finally del z is non-zero, although in the direction there is no flow, no motion, but there can be gradients. Del z is non-zero, but we neglect somehow del vr del z and del v theta del z, because first of all both of them are small, and if they are non-zero, you can actually think that there would be deformation of the disk, and that is not really welcome in a thin disk approximation in general. Okay, so with all these approximations, finally we are all set for discussing the base equations of the accretion disk, and that we will do in the next discussion. Okay, thank you very much.